Hi friends, welcome back to LGF. So this is the control system, lecture 9th. I had to start the second order system. In the lecture 8 we discuss about the first order system. First order system. To this first order system we applied some inputs and we got some outputs. The transfer function of the first order system, we have seen it was 1 divided by 1 plus tau s, where this tau is the time constant. Later we'll discuss about what is the time constant, correct? Okay, to this first order system whose transfer function is given by 1 plus tau s, we applied some inputs to it in the lecture 8. Unit impulse, unit step, ramp and parabola function. We got some outputs. Okay, then we have seen the errors also, steady state errors also in the last class. Is it okay? Today what we are going to do, today we'll do the same thing for the second order system. Correct? Second order system. We'll apply these all inputs to the second order also. We'll get output for different inputs. Correct? So before come to the second order system, we'll discuss about the LTI system, whose input is sinusoidal and output is also sinusoidal. This is important concept. There are so many questions in the GATE examination for all three branches. So let me discuss about that particular sinusoidal inputs or sinusoidal response. Whenever if you consider LTI system, linear time invariant system, the system which is linear and non-variant with time, if you applied sinusoidal input to it, sinusoidal input to this system will give you sinusoidal output. Okay, if the system is LTI system, there is a change in magnitude and phase only. What it means, if your input is A sin omega t plus theta, where this A is magnitude, this theta is phase of the input. Let me change the color over here, then we'll discuss about it. So this A is the magnitude of the input, theta is the phase of input, and this omega is the frequency in radian per second. Okay, if you'll apply this input to LTI system, it will give the same sinusoidal response, and in the sinusoidal response you will get the output A multiply with M. The function is same, frequency is same, theta plus phi m. Okay, so you can see over here, initially the phase was A, but sorry, amplitude was A, but here in the case of output you have modified amplitude, that is A multiply with M. Let me change the pen over here. A multiply with M. This M is coming extra. Similarly, the same phi m is coming in the phase. Initially the phase was theta. Now we are getting the phase theta plus phi m. Means there is a change in phase by phi m. There is a change in magnitude by m. Why we are getting these changes? Because of this LTI system. Correct? Now the question is, what is this m and what is this phi m? If you can calculate this m and this phi m, you can easily get the output of the system or not. If you provided with the input RT, and if you know the specification or the transfer function of the LTI system, you can easily get m and phi m. Here the m is the magnitude. Here it's given the transfer function. The magnitude of this transfer function is, let's take this is the magnitude, and phase of this transfer function, let's take this is the phase. Now if you want to calculate the m, this m is the transfer function at omega equal to given frequency. Let's take over here, this is omega bar suppose. So at omega bar you have to calculate the magnitude of the transfer function, or I can say the magnitude of the LTI system. This is m. What about phi m? This phi m will be your phase of the system at that particular frequency. So this is your phase. Over here you can plus or minus it. If you'll get in the minus, you will minus, or subtract it, you'll get in the plus, you will add it. Okay friends? So I hope it's clear to you. Now let me take one example based on this. Correct? So this is the question given over here. The transfer function of the system is given. See, this is the transfer function, the LTI system given over here. To this LTI system, your RT of the input is 10 cos 2t plus 45. This is the theta given. The frequency omega is given 2 radian per second. This is the amplitude given. And the question is, what will be the output of the system? What will be the output of the system? This is your question. Okay, so let's calculate. Definitely the output will be A into m cos 2t plus 45 degree plus theta m. This is your equation 1. Let's take it 1. Now you have A, definitely it's 10. You need to calculate m. So here I'll calculate m. M is nothing but, so before that you have given with the transfer function, that is s plus 2 divided by s plus 1. You need to calculate the magnitude of this transfer function. The magnitude of this transfer function will be the magnitude of s plus 2 divided by s plus 1, isn't it? So it will be omega square plus 4 divided by omega square plus 1. Correct? Now you need to calculate this transfer function at exactly omega equal to 2, because this is the given frequency of the input. Correct? So at this frequency you will get 4 plus 4 divided by 5. So this one is 8 by 5 under root. Okay, so you calculated, this is the value of m. So in this equation, 10 into 8 by 5 cos frequency as it is, 45 as it is, you need to calculate theta m also. Okay, now here is the calculation for theta m. Okay, wait a minute. So here I'll calculate the angle or the phase angle of the transfer function. So it is plus tan inverse omega by 2 minus tan inverse omega by 1. I hope it's clear to you. Okay, the phase of this is given by this, numerator will provide plus tan inverse omega by 2, and this will provide minus tan inverse omega by 1. Okay, so if you put omega equal to 2 over here, you will get TF is minus 18 by 4 3. Okay friends, so you'll put value over here. This is minus 18.43. So this is your output. Correct? Now let's start the time response of the second order system. So the order is second, so definitely you'll take this value by open loop transfer function. So this is the open loop transfer function given for second order system, and that is omega n square divided by s plus 2 zeta omega n. So here the order is 2, and if someone will ask what is the type, so type is 1. Type is given, type and order both are given by open loop transfer function, and definitely you have only open loop transfer function in your hand. Okay, so this is the unity feedback. Unity feedback, closed loop. So you can find out closed loop transfer function, and the closed loop transfer function is omega n square s square plus 2 del omega ns plus omega n square. This is your closed loop transfer function for the second order system. Now you will ask, what is this omega n? This omega n is natural frequency of oscillation. This is the natural frequency of oscillation, okay, given in radian per second. Okay, what about this zeta? This zeta is nothing but the damping ratio. Damping ratio. Okay, the factor by which we damp the oscillation of the circuit. Okay, so definitely if the response or the system is second order system, it will be having some oscillations also. Okay, so now we'll take the practical example of the second order. Earlier I told you, if you have some electrical circuit, suppose in that electrical circuit, if you have only one energy storing component, like you have capacitor in the circuit, so the order of the system will be one only, correct? So order is nothing but number of energy storing elements, correct? If you have R, L and L also in the circuit, so the order of this circuit will be 2. O for order, okay, order will be 2, correct friends? So the practical RLC circuit will see over here, practical circuit for second order system or second order or RLC circuit. So let me take the RLC circuit over here. R, here is L, and this is C. So this is the RLC circuit we have taken over here, RLC. Okay, across the capacitor I'll take the output V0 as I'm taking in the frequency domain. Okay, so I'll write it 1 by SC and I'll take this LS. Here I'll apply the input. Okay, now the transfer function for this circuit is V0S divided by VIS. So by the voltage division rule, you have to find out the voltage across this capacitor, correct? So what it will be, V0S is nothing but 1 by SC multiply with VIS divided by R plus LS plus 1 by SC, correct? So let's simplify this. This will become, you can take this VI to this side to make a transfer function. This will be 1 by SC. Here it will be RSC plus LCS square plus 1 divided by SC. This SC will cancel out to this one, and you'll be having LCS square plus RCS plus 1. Okay, now you can take LC common, so this LC will come out, you will be remain with S square plus RC divided by LCS plus 1 by LC. So can I write this transfer function equation like 1 by LC S square plus this C will cancel out this one and you will have R by L S plus 1 by LC. This is your transfer function for practical RLC circuit. Okay, you have two energy storing device over here, so this is the second order system. Okay, and we are discussing about the second order only. Now we have seen the overall transfer function of the second order, and that was the transfer function was omega n square divided by s square plus 2 del omega ns plus omega n square. Okay, so let's take it equation 1. This is equation 2. Now you can compare these two equations. Both are the transfer function of the second order system. So here omega n will be, just compare this characteristic equation to this equation. So this omega n square is nothing but 1 by LC, correct? So your omega n will be under root 1 by LC, correct? Now let's find the damping ratio. It's 2 zeta omega n equal to R by L over here. This is R by L. Let's find out the value of zeta. It will be R by 2 C by L. So we calculated natural frequency of oscillation omega n for the RLC circuit, and that is under root of 1 divided by LC. We calculated the damping ratio also for the practical RLC circuit, and that is R by 2 under root C by L. Now let's come over here. The characteristics equation of the second order system is given by S square plus 2 del omega ns plus omega n square, correct? This is the characteristic equation of the closed loop transfer function for the second order, or I can say the poles are given by this equation or not. If this is the C, this is the characteristic equation, C equation, and the transfer function of the second order system is given by omega ns square divided by s square plus 2 del omega n s plus omega n square. So this is the characteristic equation. The poles of the system is given by this equation only. So for the stable system in the S plane, all poles should be lie in the left hand side, correct? Or they should be having negative real part. Then only the system will be stable. If your poles lie in the RHS, then the system will be unstable, correct? Unstable. So if you want your system will be stable, what will be the value of this delta? If this delta is less than 0, here if this delta is less than 0, means in the negative part, definitely you will get over here your pole in the right hand side. So your system will become unstable. Okay, so for the stable system, your zeta should be greater than 0 always, isn't it? This is the condition for the stable system. In this equation, if your zeta is less than 0, your poles will be in right hand side of the S plane. So it will make your system unstable. So for the stable system, this is the must condition, that zeta should be greater than 0, correct? So for the stable system, I can give the range of zeta. Zeta should be greater than 0 and less than infinity. This is the range for stability. Okay, perfectly fine. So can I say your second order system depends on zeta? Is it okay? Your second order system poles depend on zeta value. So who is controlling your second order system output? This zeta only. Correct. So this is very important note. Please note down it, that your second order system response always depends on zeta value. Correct. So I can conclude over here, if zeta is 0, your system will be marginally stable. Marginally stable. Why marginally stable? What is the characteristic equation? The characteristic equation is a square plus 2 del omega ns plus omega n square equal to 0. Correct. If zeta is 0, you are getting s square plus omega n square equal to 0. S square equal to minus omega n square. So s is nothing but j omega n. Means at imaginary axis you are getting your poles. Over here you will get your poles. Okay, so whenever if you will get the poles at the imaginary axis, your system will be marginally stable. If your poles are in the LHS of S-plane, your system will be stable system. If your poles are in the right hand side of, let's take it, right hand side of S-plane, and this is LHS of S-plane. So here your system will be unstable. Okay, so this is the condition where, let me change the pen, wait a minute. So this is the condition where zeta is, for the unstable system I'm talking about, zeta is less than 0. This is the condition where zeta is less than 0. This is the condition where zeta greater than 0. If zeta is greater than 0, the system will be stable. Zeta is less than 0, the system will be unstable. The poles will lie in the RHS of S-plane. Okay. So in this overall discussion, this point is very important. These 2 points are very important. If zeta is greater than 0, then it will be stable. Zeta is less than 0, it will be unstable. Correct? Now, the transfer function of the second order system, Cs by Rs, is nothing but omega n square divided by a square plus 2 del omega ns plus 1. Okay, this is your system. Now to this system we are going to apply our inputs. The inputs are, will apply unit impulse, unit step, your ramp input and parabola input. Correct? We'll get the output corresponding to this. But here in the second order system we have twist, and the twist is the response is also depend on zeta value. In the first order system we don't have zeta. Okay, so the system response directly depend on the inputs only, but here it's depend on zeta. Correct? So this is all about the today's lecture. We'll discuss about this input and output relation for the second order system in the next. So in the next lecture we'll see the second order system response for these input signals. Okay, so for new updates you can subscribe the LGF. For doubt solving you can find us on the Facebook. We'll meet in this next lecture. Till then, take care and bye.